All right, pre-cal 12, let's get after it. Here we go. We're into video 30. We're into our second part of trigonometry, and our first thing we're going to look at are our trigonomic identities. So in the notes, the identities are laid out quite clearly, and they're listed, and we're going to cover a few of them here, and then we're just going to work through solving some of these, simplifying some of these. Solving is probably the wrong word, because we're just going to be simplifying. So first, everything is tied to our trigonomic ratios that we have from SOHCAHTOA, or when we get out of SOHCAHTOA, y over r, x over r. So you can see we have our sine identity, our cosine identity, right? And secant and cosecant, tan, cotan. And from those, we get what we call our reciprocal identities. And we've actually talked about these a lot, so these should be a surprise to you. Cosecant theta is 1 over sine theta. So you can substitute those for each other. Secant theta is 1 over cosine theta. Cotan theta is 1 over tan theta. And remember, when things are equal to each other, you can then substitute them for one another. So those are our first three that we're going to be using shortly here. Those are the reciprocal identities. Now from there we get our quotient identities, and these are ones that we have from this ratio scenario. Remember, sine is y over r, cosine is x over r, which becomes y over r times r over x, flip and multiply, which gives us y over x. And what's y over x? Y over x is tan theta. And then if we take the reciprocal of that idea, cosine theta, we now have x over r over y over r, which gives us x over r times r over y, which then leaves us with x over y, which is cotan theta. So we get these two identities from here. We get sine theta over cos theta is tan theta, and we get cosine theta over sine theta is cotan theta. So again, these can be substituted for one another, and those are our quotient identities. Now the next one we get is our Pythagorean identity, and we get that directly from the relationship of sine and cosine. So we saw this briefly in grade 10. Sine squared theta plus cos squared theta equals 1. So from there, we have some identities tied to that. So if we take sine squared theta plus cos squared theta, and we divide everything by sine squared theta. So it's just an algebra step. We are allowed to do this. What do we get? Well, we get 1 plus, now remember, cos over sine was cotan, so cos squared over sine squared is cotan squared, and then 1 over sine was cosecant, so cosecant squared. So we get this identity right here. 1 plus cotan squared theta equals cosecant squared theta. So that's one of our new identities, along with this one, obviously. Now we'll take that same starting point, and you can imagine what we're going to do here. Rather than divide by sine squared theta, we're going to divide everything by cos squared theta. So in this scenario, we end up with the identity sine squared over cos squared gives us tan squared theta, plus 1 equals secant squared theta. So now we have two more what we call Pythagorean identities. And these will all be listed in the notes. These are identities 1 through 8. So here are the basic ones I just summarized. Here they are, 1 through 8. This table's in your notes. Push pause here if you want to write these ones down. So now, how do we simplify identities? There are some strategies we can use that we've seen before. One of them, if we have fractions, is getting a common denominator. Now, in some of the videos, I might take this for granted, but just be aware this is what's happening. We have a plus b over c, so we need a denominator of c, so we're going to times a by c over c. That's going to give us ac over c plus b over c, so we can then write this as ac plus b all over c. That's how we do it algebraically. We do it the same way using trig. So now we have sine x, but we need a cos as a denominator, so we're timesing it by cos x over cos x. Exactly the same way we got a common denominator for fractions in grade 9. So then we get sine x, cos x, plus sine x all over cos x. So that's common denominator. Works exactly the same for trig as it does for algebra. What about factoring? Well, It's exactly the same in algebra as it is in trig. So here we have 4 minus x squared. Well, that's a difference of squares. So we have 2 minus x times 2 plus x. So on the right, we have 1 minus cos squared x. Well, that's a difference of squares. We end up with 1 plus cos x times 1 minus cos x. It's exactly the same. Another example is if you have x squared minus z squared. Again, that's a difference of squares. So we're going to have x plus z, x minus z. Same if we have this scenario, sine squared theta minus cos squared theta, theta x doesn't really matter. That is a difference of squares. So sine theta plus cos theta times sine theta minus cos theta. So we can simplify trigonomic statements exactly the same way we'd simplify algebraic statements. Another really helpful one is writing everything in terms of cosine and sine. When you can do that, it just allows you to get things into a more manageable formation. So in this case, sine is already sine, but cosecant is 1 over sine. And then cos is already cos, but secant is 1 over cos. And now remember, we would flip and multiply these things. So now you would have sine x times sine x plus cos x times cos x, which gives you sine squared x plus cos squared x. And there is one of our Pythagorean identities. That equals 1. For the second example here, we have tan x over secant x. So remember, tan is sine x over cos x, and secant is 1 over cos x. Flip and multiply, you end up with sine x over cos x times cos x over 1. The cos x's will cancel, and you're just left with sine x. So we can simplify in that way as well. The last sort of helpful piece for simplifying is using the conjugate, right? In algebra, the conjugate was when you write the exact same numerical scenario in the denominator, but in opposite sign, because that basically gives us a difference of squares factored, which will cancel out our radicals in the denominator in this case. Remember, what this would have given us is root 6, because the 3 is multiplying with those, minus root 21 over, but now when we FOIL this, we get 2, and then plus or minus root 2 root 7 plus root 2 root 7. So they cancel out. That's the whole reason why we picked the conjugate. And then minus 7. So that would give us root 6 minus root 21 all over negative 5. And it rationalized our denominator. So why would we do that in trig? Well, because we have identities. We have Pythagorean identities, right? So what we can do here is we multiply this by 1 plus cos x and 1 plus cos x. So on the top, we end up just with 1 plus cos x, but on the bottom now, we're going to have 1 minus cos squared x. And 1 minus cos squared x is a difference of squares, but we've combined it for a reason, because remember that sine squared x plus cos squared x equals 1. So algebraically, subtract either sine or cos from the right-hand side. Now you get sine squared x equals 1 minus cos squared x. And that is what we have right here. So we could sub that out. And in this case, it doesn't really do anything for us, doesn't allow us to simplify the equation. But be aware that that is going to be a very regular switch to do. So by using the conjugate. So now let's simplify some of these. So for the first one, we have secant squared x minus 1. Well, secant squared x minus 1, there's an identity for that. It's identity number 7. And again, you'll have the list, so you don't have to memorize these things. This is the same as tan squared x. So now we have tan squared x times cotan squared x. Now you might be tempted to turn everything into secant and sine and cosine. You could, but we also have our reciprocal identity, tan squared x times 1 over tan squared x. And now you'll see those cancel, and we can actually simplify this thing all the way down to 1. For the example on the right, okay, 2 cos x, can't really do anything to that. 1 minus sine x. That was exactly from what we just looked at on the last slide. We take our Pythagorean identity, so you subtract sine x on both sides, you get cos squared x. So now we have 2 cos x over cos squared x, and then one of the cosines on the top will cancel with one of the cosines on the bottom. So then we have 2 over cos x, and that is a reciprocal identity we can write as 2 secant x. So we have simplified that scenario. We're going to do a few more here. So you can see here, this is one where it's like, hey, common denominator, because we're adding. So we're going to need a common denominator. So I always used to use the term, well, what's missing? Well, we're going to need on this side a 1 minus cos x, top and bottom, because that will give us a common denominator. And here we need a 1 plus cos x, because now we have a common denominator on the bottom of 1 plus cos x times 1 minus cos x. So now top left, we're going to have sine x times 1 minus cos x, and then plus sine x times 1 plus cos x. And on the bottom, we're going to have 1 minus cos x times 1 plus cos x. Now, if we simplify this through, what do we have? Well, we have water bomb in, so sine x minus sine x cos x, and then plus sine x plus sine x cos x. I'm running out of room here. And then on the bottom, we end up with 1 minus cos squared x. Now you'll notice this negative sine x cos x cancels with the sine x cos x. So now we have sine x plus sine x over, and here again, Pythagorean identity, that is equal to sine squared x. So now we have 2 sine x over sine squared x. And again, sine x cancels with one of the sine x's on the bottom, which gives us 2 over sine x, which can simplify to 2 cosecant x. And we are done. So getting a common denominator there is a good place to start, and it actually ties in the conjugate as well. Another one. So again, common denominator. When we're adding and subtracting, it's helpful to get a common denominator. So what do we need this time? Well, on this side, I need a 1 minus sine x. So top and bottom. And on this side, I need a cos x, top and bottom. So we'll FOIL the top here as well. That's going to give us 1 minus sine squared x, and then minus cos squared x, all over cos x times 1 minus sine x. And now remember that 1 minus sine squared x is cos squared x, or you could factor out the negative from here and here, and you'd have sine squared x plus cos squared x. Let's do that. So what we have is we have 1 minus, factor out the negative, it becomes sine squared x plus cos squared x. Now, it doesn't matter which way you did this. The answer would be the same in the end. And on the bottom, we have cos x times 1 minus sine x. No point really multiplying the denominator. So now remember, Pythagorean identity here, this equals 1. So we have 1 minus 1 over our denominator. I'm not going to write it down. We've seen it. Because we get 0 over our denominator, which is just 0. So again, we've simplified as far as we can. So by using identities, you can see that things simplify quite clearly, and oftentimes all the way down to simple things like 1 or 0. That's what we like to throw at you. So let's look at just a couple more. So here we have sine x, cos x plus sine x. Okay, well, let's first look for common factors. On the top here, I have a common factor of sine x. So I'm going to factor that out. Sine x comes out, and I'm left with cos x plus 1. Now let me just pause for a second and say, these are the types of things that are kind of like puzzles, trial and error. Try something. See what happens. Did it simplify out? If it didn't, maybe you made an error, or if it didn't, you might have done just the wrong step at the wrong time. Start again, try again, okay? I'm doing these. I've done them many, many times, so I know my first step. It's okay to take some time to think about what it is you should do first. And it's also okay to just try some things and see what happens. So on the bottom, I'm going to factor out a cos x, and then I'll just rearrange those statements so they look a little bit more friendly to your eyes, because here we have cos x plus 1, and obviously 1 plus cos x is the same as cos x plus 1. Just rearrange, because now you can see that those two things are identical. They will cancel as common factors. We're left with sine x over cos x, which is just tan x, and we are done. So, last one. Determine the restrictions on tan x plus secant x for the domain of one full rotation, 0 to 2 pi. Now, what are restrictions? Well, restrictions occur when our denominators are 0. And in this case, we don't have denominators. But guess what we do? Because tan is sine x over cos x, and secant is 1 over cos x. So in this case, the only denominator we need to concern ourselves with is cos x. So we ask ourselves, when is cos x equal to 0? And if we think about when that occurs when our x value is 0, which occurs at pi over 2 and 3 pi over 2. So our domain restrictions for this is x is not allowed to equal pi over 2 or 3 pi over 2. That is our domain restriction. Now let me just do one amendment to this question, and let's just say, just so you can see how this would tie together if this was cosecant x, because that would change our denominator scenarios, because now we would have denominator of sine x and cos x. So then in this case, where is sine x also negative, or also 0, here and here? So in this case, we would actually get our quadrantal angles of 0, pi over 2, 3 pi over 2, and pi. So all of those things are restrictions because we are not allowed to have 0 in our denominator. So that's part 1 of trig identities. Part 2, 7.2, we are going to prove why one side of an equation is equal to another using our trig identities. It's good fun, it's a big puzzle, and it's probably one of my most enjoyable sections. So I hope this one made sense. Remember, you will have the list of identities in front of you, so don't stress that you need to memorize these things, but the more you use them, the more regular they will become. Thank you so much, and I will see you next time.